Well, hi there. Today, lessons 22 through 24 from Saxon Algebra 1. And what you're focusing on today is this concept called equations. Equations are the basis of most of what you do in algebra. So we're going to get to that. I want you to note that the beginning of the word equation is the same word that we use for equal. Okay, so all equations, I want you to think of it this way. If you remember a balance scale, remember those old-timey balance scales that kind of have like a stand and then they have a little tray here and a tray here. Since we live in gold country here in Placerville, you can think of, okay, you've got some gold here and then you have some weights over here. And so you figure out, if it balances, you figure out how much the weight is that gold when they're even. So equal means this is equal to that. Okay, every equation you see in math is basically this equals that. And if you could think of it that way, it will really, 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 really help you. Instead of using a balance scale, we say this thing is equal to that thing. Okay, so equations always have a equal sign. Okay, there's another sign. This means not equal. And you're used to seeing that. For example, you go down the road and you see a sign that goes like this, and it's a right-hand turn, and you may see a line that goes through it, and it says that means no right turn or no U-turn, and they'll have these lines. So this means it does not equal, or a line through something means don't do it. Okay, then there's also this, which is greater than, for example, 8 is greater than 5. Duh. So 8 is not equal to 5. Duh. 8 is equal to 5. No. So an equation has to be true or it is a bad equation. So you're always saying what is true. And then there's, of course, less than. And then there is also going to be greater than or equal to or less than or equal to. Everybody has a different way to remember that. I remember that because of the number line. Okay. Numbers going this way are greater than. Numbers going this way are less than. Notice the arrowheads on my number line. So 8 is greater than 5. Excuse me, I sneezed. Anyway, that's the basic words to it. Now let's see how you actually are going to use it in algebra. So what you're going to see is you're going to see a simple question. For example, 5 equals 4 plus 1. This is an equation. Is this true? Yes. Okay, that's your basic equation. It is called a regular old equation. Now, what about 5 equals x plus 1? Is that true? And your answer is, oh. So the answer is yes, if x was equal to 4, that would be true. This is called a conditional equation. Conditional. So what you're looking for when you see this in algebra is you're looking for under what conditions is this true. Again, equations are always this equals that. The left side equals the right side. They are balanced on a scale. And so if you have a letter in here, that means it's an unknown, it's a variable. You're always trying to find what condition is going to make this true. And so that's what we look for. And so how you'll see this in lesson 22 is they will introduce this concept of conditional equations. We never use it. We just call these things equations, but it's a conditional equation. It's only if this is true, will that make it? And again, that's kind of the whole point of algebra, is you want to find out what conditions or what is going to make this true. So when we look at lesson 22, you'll see a problem like x minus 2 equals 0. And they'll ask you, does negative 2 satisfy this equation? EQN is equation in abbreviation form. So does negative 2 satisfy this equation? Well, I don't know. If what that means is if x was negative 2 minus 2, does that equal 0? And the answer is nope. So negative 2, does it satisfy this equation? The answer is no, it does not satisfy the equation. What about does positive 2 satisfy the equation? Well, let's try it. Positive 2 minus 2 equals 0. Is that true? Yes, this is true. So therefore, yes. Uh-oh, I'm in trouble now. I made my page go weird. Okay. Anyway, does that work? I don't know. The answer is yes, it does. That's lesson 22. Does this satisfy the equation, yes or no? And so let's go on to what about lesson 23? What is that all about? Lesson 23 is saying, what are some of the basic rules of equations that are always true? So, for example, if I use an equation like 3 plus 2, there's a rule when you're adding things together that it does not matter the order. You can, it doesn't matter. There's also a rule that is, what if I have is if 3 plus x forget the 3 plus x. It just means that, well, let's try this. If 5 is equal to 5, true or not? Yes. If I add an x to this side, are they now equal? The answer is no. I would have to add an x to this side. Your book calls this the additive property of equality. I don't want you to memorize that particularly. What I'm looking for you to do is understand this concept that if you do something to the left side of an equation, you must do the same thing to the right side of the equation or it won't stay equal. All right, let me go back to this balance scale concept. So let's say I had a little brick of gold on this side, and that was equal to 2 of these little weights. Okay, if I add a cup of coffee to this side, will they stay balanced? And the answer is no, this will go down because I have now gone, even though this one and this one were the same, by adding the little cup of coffee, it's not going to work. But if I add the same size cup of coffee over here on this side, it'll balance itself out again. So if I have something that equals something else, if I add something, subtract something on the left side, as long as I add or subtract something on the right side, it's still going to stay the same. This is what we call the additive property of equality. It means that you're adding the same to both sides, it's going to work. So let's see how this might work itself out into a problem. I'm going to show you how you should be looking at algebra problems. So for example, let's say you've got x plus 5 equals 17. If I think of this as a balance scale, again, and I've got this thing on the left and this thing on the right, and they're balanced, that's true. What I want to ultimately get to in the equation is I want to know what x is equal to. What's going to make this work? Well, obviously 12 plus 5 is 17. So x is going to be 12. But let's figure out how we do it, thinking of it as a balance scale kind of concept, or what they call the additive property of equality. Okay, if I want to get this by itself, and again, think of this as a jar of gold and this is a bucket of coffee. Okay, to get rid of the coffee, all I have to do is just remove the coffee from that side. Because what's positive 5 minus 5? The answer is 0. I will end up with just x. Well, if I subtract 5 from this side, I must also subtract 5 from the other side. And I end up with x equals 12. Isn't that handy? So whatever I do to the left, I'm going to do to the right. And that works with fractions too. So let's say, for example, I'm going to do something that looks a little bit harder, and but it really isn't. So let's say I have something like d plus 4 1/7, and that's equal to 3 1/6. This is one that you wouldn't do in your head typically. You'd say, I don't know. I want to know, what is d? What am I going to have to add to 4 1/7 to give me 3 1/6? So I think about it a little bit and I go, well, 4 1/7 is bigger than 3 1/6. So this is going to have to be a negative number for this to work. Well, I don't really care if I'm doing this in algebra land and I'm thinking, oh, balance scale, this thing and this thing. If I just subtract 4 1/7 from this side, and I subtract 4 1/7 from this side, I'm going to end up with d equals, because 4 1/7 minus 4 1/7 is 0, I'm just going to end up with d on this side. And over here, now I have 3 1/6 minus 4 1/7. Well, I'm going to do and change this into 19/6. Remember, 3 times 6 is 18, plus 1 is 19. And I'm going to change this to 4 times 7 is 28, plus 1 is 29 sevenths. Okay, and now I go back to my arithmetic that we had been working on all year. Do the denominators, are they the same? No, they are not. To make them the same, I must multiply top and bottom times 7, multiply top and bottom of this one times 6. Now they are the same. So 6 times 7 is 42. 19 times 7, you take your calculator out and you go, what's that? 20 times 7 is 140, so 19 times 7 would be 133. 29 times 6, I'm not going to do that one in my head. 29 times 6 is going to equal 174. And then so 174 from 133 is going to be negative 41 over 42. And so that's what d is. You never would have just guessed that, but just by not having to do much other than think the left side and the right side have to be equal, and then you end up with a fraction thing, which you can use a calculator for. You can go ahead and get the answer fairly simply. And so whether it's a fraction or whether it is a regular old number, that is what you're looking for on what to do when you are adding fractions on the side of an equation. So let's look at another thing that you notice. And again, I've said it, but I'm going to say it different. Let's say I have something like 2/5 x equals 7. And I were to say solve. What I mean by that is, what number is going to make this work? Well, in multiplying, I don't do the same as just adding and subtracting, but I still am using the concept of a balance scale. The left and the right have to be equal. Whatever I do to the left, I have to do to the right. So what I'm looking for is, what can I do to make that just have an x? Well, here's what I can do. If I multiply this times the reciprocal of this number, what's 5 times 2? It's 10. What's 2 times 5? It's 10. What's 10 over 10? It's just 1. What's 1 times x? X. And so by taking this times the reciprocal, I win. I can get rid of it on this side. But again, whatever I do to the left side, I have to do to the right side. Well, what I do on the left side, I multiplied it times 5/2. Well, it's 7 times 5. It's 35 over 2. So, or in other words, 35 over 2 is the answer. That's what x is. I do another one, did that one a little quick, but let's say you have something that's a mixed number. 3 1/5 times y equals 32. Okay, here's one where I didn't use x, I used y instead. And I did a mixed number. This is why in algebra we don't do mixed numbers. 3 times 5 is 15. This is 16 over 5 equals 32. Notice now I have a simple fraction times a letter equals a number. And I want to know what is y. Well, multiply both in top and bottom times 16s. And what's the 5s will cancel, the 16s will cancel. I'll end up with just y. Also, 32 is 2 times 16, right? So 16s will cancel, and I'll end up with 10. 2 times 5 is 10 over 1. So that's the answer. And I never would have guessed that just looking at it, but just by using the balance scale concept where the left side is equal to the right side, and whatever I do to the left, I do to the right. And again, I'm choosing to do something to get rid of this number in front. Okay, one last review just to clarify one more time, because this is a very common mistake. Do not feel bad if you make this mistake, but fix it. There is a difference between, let's say, 2/3 plus x equals 7 and 2/3 times x equals 7. If I'm going to solve this one, I'm wanting to get x equals something. How do I get rid of this 2/3? Well, if I subtract 2/3, well, what's 2/3 minus 2/3? 0. I must subtract 2/3 here. 7 minus 2/3 is 6 1/3. Okay, so, and that makes sense. 2/3 plus 6 1/3 will equal 7. That's very different than here. What do I do to get rid of the x? I must multiply it times the reciprocal of the number in front of the x. Because 3 times 3's will cancel, 2's will cancel, or 6 over 6 is 1, and I end up with x equals 7 times 3, which is 21 over 2. We always leave them in this form. We never say, oh, this is equal to 10 1/2. That's lame. Always leave it in fraction form. And that is lesson 24. So enjoy your math, and I will see you in class.